What I want to do is I want to go over an example of the analysis that you would use for the magnesium oxide lab that we did in class today to show that Hess's law is correct, or to demonstrate that we can use Hess's law to get the enthalpy change for a target equation. So here what I have is I have three equations where I am reacting my compounds together. In my second equation, I'm just dissolving my potassium hydroxide in water. And I want to show that two of them add up to the third. So what I'm going to do is I'm going to show how equation 1 and equation 2 add up to equation 3. Now, just like we talked about in class, the first thing to do is identify each of the things in equation 1 and in equation 2 in our target. Then we're going to look to see if they're in the correct side of the equation for our target equation. And we can see this for both equation 1 and equation 2. As well, we would check the coefficients, and they're both correct. So for both of these examples, we would see that I would just multiply the equations by 1. Okay, and I can add them together, and I would cancel out the entities that are found on both sides of the equation, and I'm able to show that if I add equation 1 plus equation 2, it gives me equation 3. This means that the enthalpy change for my third equation is equal to the sum of the enthalpy change for my first equation plus my second. I now use this information to conduct a number of calorimetry experiments where I'm going to combine solid or aqueous potassium hydroxide with my hydrobromic acid, or I'm just going to dissolve some potassium hydroxide in water. And I measured the temperature changes for each of these reactions or state changes. And now I'm going to use this information to first determine the enthalpy change for each of the reactions I had above. Now that I know that my first two equations can add up to my third, what I'll do is I'll take my information and I will look at the enthalpy change for each of the reactions independently. So here I have my combination. As we do for calorimetry, we identify our system and our surroundings, identify that it's an exothermic system because my temperature of my surroundings went up. So delta H is negative Q. And then I can solve for the enthalpy change of this reaction. Now, because this gives me a molar enthalpy for this reaction so far, I now have to take this molar enthalpy and multiply it by the coefficient in my balanced equation. And that now gives me my enthalpy change for my balanced chemical equation. Okay. Similarly, for the dissolving of solid potassium hydroxide in water, I identify my system, my surroundings, the fact that it's an exothermic, how I'm going to calculate my energy change or enthalpy change for each my system and my surroundings. Then I can solve for my unknown. And again, I get my molar enthalpy from this, and I have to turn it into an enthalpy change for my balanced equation by multiplying by the coefficient. And finally, we'll do it for our third reaction, even though this is our target equation, since we have data. Okay, and we have our similar calculations where we identify our system, our surroundings. We identify that it's exothermic, so delta H is negative Q. How we're going to get our enthalpy change for each of them, and then we just combine and solve. And then finally, I take my molar enthalpy and I multiply by the coefficient of my balanced equation. Oh, and this is a typo. It should be minus 56.0. Okay, so now I know my enthalpy change for each of my reactions, and I had shown previously that if I add equation 1 plus equation 2, I get equation 3. So therefore, if I add the enthalpy change for my first two equations, it should be equal to the enthalpy change of my third reaction. So I add them together. I can see that I get pretty close. And I could quantify how close I am by looking at my sources of error and calculating my percent error. Okay, and so I'll calculate my percent error, treating the enthalpy change that I got for the third reaction as my actual value. And I can see that the adding of equation 1 and 2 gets me within 1.49% of the enthalpy change I calculated for reaction 3. And the reason it's not perfect is because my sources of error. Now, all I'm going to say about this is I will point you to your assumptions of calorimetry as a good starting point for sources of error. Okay, and saying human error we didn't measure properly is not a good source of error. But look at the assumptions that we're making when our reactions are occurring and the meaning of those assumptions.